Okay, so we have a function f of x that has range 5 over 10 over the interval -10 to 10. So we know our interval, it's going to be from -10 to +10. And then we know the range is going to be from 5 all the way to 10. So what is the range of the function defined by g of x is equal to 2 times f of x plus 5. So when answering these types of questions, you want to think about, okay, what is this 2 doing? And what is this 5 doing? Here is an example of what it might be doing. So here's my function f of x, and it's this one in red. And now let's graph g of x, where I have a, b, and c to be just some variable, some variable we could change. So if we change a, what do we see going on here? It's gonna be a vertical stretch. See, if I have the 2, we are stretching it from 5 to 10. Now we're going from 10 to 20. Right, so we're multiplying our range by 2. Okay, and what about if I change our c? Our c would be our 5. This is just going to be a shift. It's not going to be multiplying our range. It's not going to be stretching it. It's just going to shift it up. And if we do 5, our new range is in from going from 15 to 25. Okay, but what if it's inside our function? What if it's inside here? In this case, we don't have anything inside, but if we have something inside, this doesn't change our range. It just shifts it to the left or to the right. So going back to this one, our 2 is going to be a vertical stretch by positive 2. Okay, and then our 5 is going to be a vertical shift by positive 5. So notation wise, if I take my interval 5 to 10, right? If I multiply it by 2, and then I add 5 to my interval. So we got to be careful on how it's very similar to how we go about doing PEMDAS. We don't want to add 5 and then multiply by 2, because if we did that, you're essentially changing it before you apply the multiplier. So here, since the 2 is first, we do that first, and then we do the add 5. It's the same if we do 2 times I don't know, x plus 5. Right, this implies 2 times x, and then you add 5. It doesn't mean x plus 5 and then multiply everything by 2. So going back to this, 2 times 5 will give us a range of 10. 2 times 10 gives us a range of 20. So this is our new range if we multiply it just by the 2. And then we're going to shift everything by 5. We get 15, 25. Okay, good. Now for number 2, I saw a lot of different answers, and I'm going to go over one possible solution. So f of x, we have f of x, we have g of x. We want to find a composition of f g of x, or f o g, and g o f. So let's look at the composition of f g of x. So the way I like to write this out is, okay, I have g of x, right? And now I just start substituting in. And I do it one at a time, f, but we know what g of x is. G of x is x minus 1. And now we're just plugging this in. So we look to our function f of x, and whatever we replace, wherever we see an x, we replace it with what we're plugging in. So since it's just x squared, we're going to have x minus 1 squared. And if I FOIL this out, I will get, what is this? X squared minus 2x plus 1. Yes. Okay, that's my first one. Now let's look at this one. G composed with f of x. So again, g, but I'm not going to write x minus 1. I'm going to write x squared. Okay, and then look at my function. And every time I see x, I'm going to replace it with x squared. So here it would just be x squared minus 1. And here I can't FOIL anything out. I mean, this is a difference of squares, but that's not going to help us. Okay, so the question is, for which values is it true that this f g of x is equal to g of f of x? So we know what this is. This is just this. X squared minus 2x plus 1. And we know what g of x composed with f of x is. It's just this. So what I can do is make them equal to each other. So more explicitly, if I do f of g of x is equal g of f of x. So when is this equal? Well, let's substitute that in. F of g of x is x squared minus 2x plus 1. It's equal to g of f of x. So that's this one. So that would just be x squared. Let's start moving stuff around. Let's move this over. But if I move this over, minus x squared, these cancel. So those cancel out. I am left with 2x plus 1 is equal to negative 1. Okay, we have an x. Let's try to get x by itself, because that's what we want. We want to find all values of x. So let's see. Subtract 1 from both sides. I get negative 2x is equal to negative 2. And then divide by negative 2 on both sides. I get x is equal to 1. So this statement is only true for x equals 1. Okay, good. Why is this shaking so much? Okay, so f of x is a continuous function and g of x. Oh, f of x is a continuous function and the graph y is equal to f of x has a relative maximum at 1. Okay, it's a relative maximum, so we know 1, 2, 3, 4, and then 1. It's going to look this. And let's assume it's something like this. Oh, this is our vertex, or our maximum. So 1, 4. Okay, at what point does the graph y f of x plus 1 minus 2 have a relative maximum? Okay, so this is another transformation question. So remember from the very beginning, if it's in top, if it's inside our function parameters, it's affecting our left and right. So to figure out what this is, x equals 1, we set it equal to 0. So this negative 1 means left shift by 1. Okay, so we're going to go to the left one. This negative 2, well, that means it's going to be a vertical shift by -2. So it's going to go down. Down. So if we look at this point, we look at 1, 4. We go left by 1. That's going to change our x-axis. We're going to go 0, 4. Then if I apply the vertical shift, by -2, I'm essentially going down. So I'm going to change my y by going down 2. So this turn into 0, 2. This is my new relative maximum. Okay, number 4. If f of x is defined by this, then find the inverse. So this is an inverse question. So let's start by writing our question, x plus 1, x minus 1. So first, you got to recognize that f of x is just our y value. So let's write it as y equals x plus 1, x minus 1. And the key part to finding the inverse is 2 steps. We're going to, number 1, swap x and y's. And this is for finding all inverses. Swapping x and y's. So here, I'm going to swap my y's with x and my x's with y's. So we're going to write x. And on the right side, I'm going to write y plus 1, y minus 1. And then step number 2, solve for y. Okay, so we want to solve for y. Well, this is in the denominator, so I'm going to multiply by y minus 1 on both sides. Y minus 1, these cancel out, and then I just throw this out. X times y is just xy. X times -1 is negative x. And then on the right side, since these cancel out, I have y plus 1. Now we want to solve for y, so let's get every term that has a y. This doesn't have a y, so I'm going to move it over. This has a y, so I'm going to move it to the left. So minus y, and then plus x, plus x. So this cancels, that cancels, and then I get y like this. I wrote it on the right side. And then 1 plus x. Okay, now since these two have y's, I could factor it out, x minus 1. And we get 1 plus x. And now, last step, I want to divide this, because I'm going to get y by itself. So we have 1 plus x, or x minus 1, or if you like your x's first, you can do x plus 1, x minus 1. So either of those work. And then it's not asking us for, I wasn't in frame. Okay, so f of x, we write it as x plus 1, x minus 1. And then y is x plus 1 over x minus 1, right? So f of x is just our y, so we rewrite it with y. And then our two main steps is swap your x and y's, and then solve for y. Okay, so we swapped our x and y's. X is equal to y plus 1, y minus 1, and then multiplied everything, forward that out, solve for y. Okay, and this would be our f inverse of x. Okay. All right, number 5. Which of the following has a removable discontinuity at or a whole at this point. So here, our x value is equal to 1. So that means either x minus 1 is equal to 0. So what that means, x minus 1 has to be in the bottom, right? And then we can have stuff up here. But if I just have x minus 1 and it's not getting canceled by anything, this becomes an asymptote at x equals 1. So at x equals 1, we have a whole. I mean, a asymptote. And it could look something like this. That's not what we want. A asymptote is very different from a whole because it doesn't act like this. It doesn't act like a border. It just takes that point out. So here, x minus 1, is it being canceled by anything on top? No. So this is the asymptote at x minus 1 at x equals 1. Here, let's do this. Let's try to combine everything together. So we have 1, so I'm going to write this 1 over 1, and then multiply by x times x, because we need to get the same denominator. We get x over x plus x over x. Since they have the same denominator, we write x, and then on top we have 2x. Here, we have a whole for which the x value is equal to 0, right? We set the bottom equal to 0. And then, well, there's nothing being multiplied, there's nothing being subtracted. So we're done. X minus 1. There's a whole at x equals 1 because it cancels both the bottom and the top. These x's cancel. So there's a whole at x equals 1. Here, the top expression, x squared minus 1, can be rewritten as a difference in squares. So meaning x plus 1, x minus 1, and then let's rewrite it with x minus 1, x minus 1. Here we have this expression and this expression canceling out. So that means there's a whole at x equals 1. So the only possible answer would be C. Okay. So now, number 6. Find the vertical asymptotes of the function f of x. So on the bottom, so whenever we're looking for vertical asymptotes, we always want to look at the denominator of our expression. So here we have x plus 4. Oh. So this is going to be x plus 4 is equal to 0. So x equals negative 4. Okay. Then x minus 10 equals 0. You get x is equal to 10. So remember, vertical asymptotes are equations, right? It's a vertical line at negative 4. This is my x. No, this is my y. This is my x. And then over here somewhere at 10. They're vertical lines. They're an equation. Okay, so number 7, 7a, another composition function. So we're going to write f of g of x. Okay, and we're going to do the exact same thing we did before. F of x squared minus 2. So what that means is x minus 2, I'm going to plug this in to this function right here, or f of x. And every time I see an x, I'm going to plug it in. So I'm going to write f of x exactly how it is. 1 over and give myself some space, 2. And then here, we would write x. But since we're plugging x squared minus 2, I'm going to do x squared minus 2 right there. Now, is there any numbers being multiplied or is this being squared? No. So we could remove the parentheses and we get x squared minus 2 plus 2 all over 1, or all under 1. Minus 2 plus 2 cancel out. We get x squared in the denominator. Okay, the domain of this. So what values can I not have? Well, let's set it equal to 0. So x squared equals 0. Take the square root, we get x is equal to plus or minus 0. Well, plus or minus 0 is the same thing, so x equals 0. This is the only value we cannot have. So we could write it multiple ways. We could write it as all numbers except 0. Or you could write negative infinity, right? Going from negative infinity all the way to 0, skip 0, and then continue to positive infinity. So either one works, this one or this one. Both are good. So now, finding the inverse of g of x. So we write g of x is equal to x squared minus 2. We write it with y is equal to x squared minus 2. And then step 1 and 2. Step 1, swap x with y's. Let me get this in front. And then number 2, solve for y. Okay, so we got to swap. So then our next step is x is equal to y squared minus 2. Let's solve for y now. So let's move this over. Actually, I'm going to write it y squared is equal to x plus 2. So this is x plus 2, added 2, but I wanted y on the left side. Okay, from here, I'm going to take the square root. I get y is equal to plus or minus x plus 2. So here, we are getting two functions. We are getting y is equal to positive square root of x plus 2. We're going to get y is equal to negative square root of x plus 2. So technically, this has no solutions because we're getting two functions and we should only be getting one function. Inverse exists only if you get one function. We're getting two functions. We're getting a positive function and a negative function. But for the sake of this test, we're going to go with the positive one. And let's pretend we didn't get this. Here, what is the domain of this function? What is the domain of y? Well, we know we cannot have negatives inside. So what we could do is let's look at the inside of this. The inside of this square root is x plus 2, and this has to be greater than or equal to 0 because we cannot have negative. So subtract 2, subtract 2. So x needs to be, let me write that. X needs to be greater than negative 2. That's going to be our domain. X needs to be greater than 2. Or we could write domain is, so since it's greater than or equal to, we could use the bracket here, negative 2. And what our numbers are greater? Well, that's going to be negative 1, 0, 1, 2, 3, 4, 5, all the way to infinity. So this is going to be our domain. Okay. Okay, any questions? Let me know.